Okay, we're at chapter 31. First section is 31.1, the self-inductance and inductance. Let's share the PowerPoint. And yeah, it opens up with a little drawing of things you may have seen on the road. The circles you see there are actual loops in the road. They're inductors. They're coils of wire that sense the magnetic the presence of your car. Your car is acting like a core in the coil. If you remember the experiment we did with the solenoids, if you put a metal core, you increase the magnetic field. So your car acts like a core that the magnet that the coil sense, and we'll get to that a little bit later. We're going to start off looking at a circuit. After the switch is closed, the current produces a magnetic flux through the area enclosed by the loop. In other words, the little rectangular circuit there is a loop in itself, and as the current increases towards its equilibrium value, the magnetic flux changes in time and induces an EMF in the loop. If you recall Lenz's law, as the magnetic field is increasing, it's going to try to induce a reverse magnetic field, and it induces its own EMF in the loop just from the changing magnetic field, based on Lenz's law. Now let's look at the equations. The induced EMF is the negative of the time rate of change of magnetic flux, and the magnetic flux is proportional to the magnetic field, which is also proportional to the current in the circuit. So self-induced EMF, the self-induced EMF in a circuit always is proportional to the time rate of change of current in the circuit. I'm sorry, so that's the first, the proportion. So self-induced EMF, the EMF EL there is equal to negative L didt, didt being the change in current, the time rate of change of current in the circuit. L is called the proportionality constant, and it's called the inductance of the loop. And we'll learn that there are things called inductors. It depends on the geometry of the loop and other physical characteristics. And if you have n turns, Faraday's law says that E sub L is equal to minus n d phi dt, where phi is the magnetic flux. Now, if we relate these, L is equal to n times the magnetic flux divided by I. Now they're using a little I because it's a changing current. Okay, now the unit is the Henry. In your textbook, there's a picture of Mr. Henry. They don't have a slide of that, but there is one in your textbook, and it's equal to 1 volt second per amp. So L equals minus EL divided by didt, and just recall that R is equal to delta V over I. So it's the R is the resistance to current. L is the resistance to a change in the current. Okay. So let's see. So yes, the resistance is the opposition, is a measure of the opposition to current, and inductance is a measure of the opposition to the change in current. Okay, now a coil with zero resistance has its ends labeled A and B, with the potential at A is higher than at B. Which of the following should be consistent with this situation? If in either case, the current is not going to be constant. And if the current is increasing, remember Lenz's law, it's going to be directed from A to B. If it's decreasing, it's going to want to reinforce it, and the current, and it's going to be directed from B to A. Let's see if I'm right. Yes, the current is increasing, is directed from A to B. If the current is decreasing, it's directed from B to A. All right. And that's the end of that particular introductory section. And we'll pick up with section 3.2 RL circuits in the next one.